Okay, couple quick announcements. Homework 3 is due relatively soon, so make sure you get on that. And homework 4 is available next week, but you've got quite a while to do that, so don't worry about it. Next week, focus on the quiz, which is in the later part of the week, and then the midterm, which is available on the 13th at around midnight, and then is due 2 days later. Of course, you don't have the full 2 days to work on it once you start. Those will all be in the instruction. There'll be instructions under the assignments tab on the website for the midterm. So we'll probably put those up on Thursday. And then the queries and the multiple choice portion of the midterm will all be done through Gradescope, and there'll be instructions there for how to do it. Please don't ask any questions about the midterm on Piazza, because I won't answer them, and I will the TAs, because you answer it for one person, then you got to tell everybody, and asynchronously doing a test like that, it's a real pain. So we've worked hard to make it so that there shouldn't be any assumptions you have to make in order to answer the questions, but if you really feel compelled like there was something, then once it's done, you can add a private message on Piazza. But by and large, I don't think you're going to need to do that. And yeah, it's done using SQLite. The final will be done using Postgres, but the midterm is using SQLite. So keep that in mind. So make sure you have SQLite with the databases, and we'll tell you what databases you're going to use in the instructions, like setup, running. It's good to go because you don't want to start the midterm and go, oh shit, I got to set up the databases still, and that wastes time. So don't do that. Okay. Any questions on like the logistics of what's happening this week and next week? No? All good? Okay, when in doubt, check Gradescope, because it has the definite deadlines on there. And we'll make announcements about some of the stuff on Piazza as well. Okay, so today we're going to touch very, very briefly on set operations, because it's like a 5-minute, 10-minute part of the lecture. Most of you have already seen this stuff. It's very simple. It's just good to know about, and it kind of feeds nicely into the relational algebra stuff. We were going to do relational algebra on Thursday, but I thought, what the hell, look at the weather. We're going to be in a crappy mood, and we'll have to start with the relational algebra. So we'll dive into the beginnings of relational algebra. The reason why is I think one of my friends who's a data science manager at AWS, and one of his friends who's a data engineer at AWS are going to come down and maybe give a guest lecture. So I want to kind of make some room in the schedule for that, because I think that could benefit all of you to get some more information. But don't hold me to it. I'm still coordinating with them and getting that set up, but it will probably be around March. If it does happen in 4th or so. Yeah, so, okay, let's go ahead and get started with set operations. Set operations are very nice because they can be a very easy way to essentially kind of do what a join does in a way, and that's take two different tables and then combine them somehow, or combine some part of them. Set operations are very nice because they're based off of set theory, and you all know Python, have worked with sets, or some of you have taken logic classes and understand union, intersection. So these things are not tremendously difficult to do, but they work in very interesting ways coming at it from the point of view of joins, but they work in very logical ways coming at it from the point of view of like what set operations are. So for example, we have the union operation where we take, for example, table 1 and table 2, which has both of them have the ID and name attributes. We do two select from table 1 and table 2, select star in this case, and we union them, and then they just take all of the data that's the same and add it together, and if there's data that's duplicated, it removes the duplicates. So in this case, it doesn't matter if table 2's attributes were called ID and name. They don't need to match. What needs to match is the data type and the ordering that the table has. So if, for example, ID was an int and name was a string, table 2 could be called like ID and first name. But if table 2 had first name first and then ID, and you tried unioning them, this is sometimes a SQL dependent, but you'll get errors. So there are restrictions on the way you have to set up the data. And I will also say that table 1 and table 2 don't have to be tables on disk. They could also just be tables that were created using more advanced operations that you then try and union. It's a very nice way of working, though, because it's very clean, and it doesn't have the same, it has certain constraints, but it doesn't have the same foreign key constraints that you'd have if you're doing like a typical join. So not very difficult, it's just a union. Already talked about these duplicates could be eliminated, and yeah, they work pretty nicely. Here's an example of union being used, and I like to put these little scenarios here. So in this case, what is this one? Retail chain inventory management. Okay, so you imagine that you have two stores like, Ralph's A and Ralph's B, or Whole Foods A and Whole Foods B, or whatever. And they both have their own separate inventories, and those inventories are, let's say they're managed at the store. And those inventory tables are probably very similar in their attribute construction as well as in the data they have, but the data is going to certainly be different because they might sell different food. They're going to have different quantities of the same food that they do sell probably. So let's say that once a month, the headquarters of Ralph's or Whole Foods wants to go ahead and collect all the things that their stores sell and get like a complete list. A union would be a great way to do this. We don't know if there's some foreign or primary key thing that we can use to do joins because these two tables come from different retail stores, but the data is similar enough so we can use union as a natural way to collect that data and pull it together. So this would be like a really classic case of using a union operation. Okay, any questions on union? Yeah. Well, the output of a union statement with two different tables is another table. So you could do a where clause, like you could filter on these rows. And of course, the select product name from store A products, that entire relation, like let's say the store A table on that side, need not be on disk. That could also be downstream from filtering. But this operation kind of happens on its own. So if you were going to do further filtering and stuff, you would do that on like this new table here that gets created. And a lot of that, like how you, the syntax of this is very rudimentary and basic for the purposes of explaining to you what's happening. The implementation detail of this may be ever so slightly different depending on what relational database management system you're in. And you'll see some of this actually in a couple slides, how there can be extreme differences in one of these kind of set operations. But great question. Okay, so we're all good on union? Okay. Union all, same exact thing, except it does not get rid of duplicates. Nothing more need be said. It will just copy those over. Yeah. Okay, intersection. Intersection, same story as union and union all, except now we're in the Venn diagram where there's overlap. So in this case, a mirror with ID 3 is the only thing that intersects, therefore we keep it. And remember, since we're doing set operations, we are comparing not IDs here, but we're comparing tuples. So tuple ID 3 name and mirror is similar in table 1 as it is in table 2. So if you're going to select lots and lots of attributes to union on, and remember, if I have like 5 attributes I'm unioning on, I need 5 attributes in the other table. Those 5 attributes have to match. So as you add more and more attributes, ostensibly, you're probably going to get less and less matches for something like an intersection. So just be aware of that too. But you don't also want to have so little attributes, like unioning ID on ID doesn't really yield you anything perhaps useful, unless you're going to use an ID later on for something useful. So union, intersection, these kind of things are really great for pulling out IDs and data that might not seem very useful to then use later on in further joins or other conditions, or to do something where you want to try to get like unique IDs, or sorry, unique food types like in the previous example, or like for the intersection thing. This would be like music streaming service. So an example for this would be like, let's say you work for, I don't know, MySpace or something that has like, music lists. Not Spotify, because I'm going to use Spotify later on as an example. I can't reuse them twice. But let's say that you want to, you have users that have, multiple playlists. Playlists can have the same music in it, right? Like it's not like if I put one song into a playlist, I cannot put that song in another playlist. So a user has multiple playlists, and let's say that we want to create one unified playlist, which is the intersection of two playlists. This would be intersect would be a perfect operation to do that. So yes, we can make the DSC100 mix. Running high and dancing. Full disclaimer, I got ChatGPT to create these track names. So Night Fever and Groove On and Electric Vibes were, I thought, excellent. Okay, so intersection. Any questions in intersection or intersect? None? Okay, stuff should all be very familiar. So I'm just kind of going through it because relational algebra is the stuff that's definitely going to be new. Okay, minus, where stuff gets a little bit interesting. So minus really depends on which, it's like a left join in the sense that it matters what table you're describing first in this operation. And it's going to just keep the ones that are unique to that table that are found. So for example, Amir is in both table 1 and table 2. So he gets pulled out and we only have ID 1 and ID 2 in the resulting table. Minus is not supported in all SQL databases. The except keyword would be the other similar keyword that's typically used in other relational database management systems. So minus and except are the same thing. They're just except is that you're probably going to run into except, not minus, unless you start working with Oracle. I believe Oracle is except. Okay, so an example of where you might want to do something like this. You have an e-commerce platform and you want to see what products have not received reviews yet. So you can have your products table and then your reviewed products table, and then you use a minus, and that gets you obviously the products that are in your products table that do not show up in your reviewed table, and that gives you all the products that have not been reviewed. Again, you could probably do a join for this too, but if for some reason reviewed products doesn't have that foreign key consistency in there for some reason, maybe you just has like a product name, or maybe there's a product SKU in all products that's in like the description, and that product SKU is a primary key in the reviewed products table. You couldn't do a join necessarily unless you're going to do some like, futzing around with the data and then updating a table. You don't want to do that. So in this case, this is where like the minus or the except operation could really help you. Is for these kind of things. I have a okay. Any questions on minus or except so far? Conceptually, we understand how all this works? Okay, so how could all this stuff be useful? Like, let's say you work for Spotify and you want to, do some machine learning thing where you want to create a playlist for a group of people. Let's say 16-year-old teens or something, whatever the hell they're listening to nowadays. How would you do that? You could create some fancy machine learning algorithm, right, that takes in all this information and attributes and data. You've got to build an orchestrator or a pipeline. You've got to validate it. You've got to have training. I mean, this is a nightmare to do this. What might be a really easy way to use set operations to create probably a pretty good baseline model of what playlists you would want to have for 16-year-old teens, maybe living on the West Coast or something. Right? So you could take the union of, so all of your users who fit that category, you could take all of their like songs, you could union all of them, and then you could take all of those like songs and get the intersection of them, and then minus that complete list from the intersection. So you have the complete list of songs that are liked, and then you have a list of songs that are liked by everybody. So you have one song that's extremely popular, everybody has liked that song, you want to remove that song from this playlist recommendation because you don't want to recommend people maybe everything that everybody else likes, but you want to recommend them kind of like stuff that a lot of people like, but is very sort of maybe obscure. And so you can use intersection to remove all the stuff that everybody likes and then have a list and then rank that list or limit it or something. And now you have a list of songs after the minus operation, which includes songs that are liked by a lot of people that meet that group, but isn't liked by everybody. So it kind of gives you a nice little baseline model without doing any machine learning that you can use. So what I'm trying to say about this, I don't know, it just came up at the top of my head, is that SQL and set operations and these kind of things allow you to do very powerful things, and you can use them in very powerful ways. I'm not saying it's going to be ever as good as a machine learning model, though it might be if the person who's doing the machine learning model doesn't know what they're doing, but it does allow you to have a nice way to create data products without having to do a bunch of stuff. It can be a very quick way to get work done. So there is a place for SQL in these kind of problems, at least, especially for like baseline stuff. Okay, so here's just a list of sometimes you might want to use set operations over joins because, again, they are very similar. The most important one is when you just can't use joins because there's not a foreign key that you can use. If there's no foreign key, then you can't use the join. So set operations becomes very nice. Set operations can also be quicker sometimes depending on the operation and implementation of the database you've created in the relational database management system. That's true. And this interoperability idea as well, where it's just highly portable. You can use it in a lot of different cases. You don't have to have all these all this setup. And it translates very nicely also over to Python and pandas and stuff, where you can do all these set operations very easily as well too. So the logic for it is highly reusable. That's all we have for set operations. Set operations, as you can see, are not tremendously difficult. But is there anything that is unclear? Yes. Okay. Caramel muffin. If you want to get the counts, the stock counts. So if you wanted stock counts, that could be a little bit more difficult. But yeah, you could get that. So you're saying you want to take the store A and store B, and then you want to take the product name and then the count of the stock. So first of all, we're assuming that product name can't be duplicate in any table, so they're all unique, right? So we're trying to get stock count across the entire database. So the first thing you would do is get this product name table right here, and then go back and join it into all these other tables, and out of those tables individually grab the counts and add them. You might be able to force that in the union statement, but I don't know how that exactly works. We could try it out maybe in the demo if we got some time.
Union will remove duplicates of the tuples. It's not just one thing. So if you were to do union for the whole table and not just the product name, in this case, then it checks the union of like the whole tuple. So your product name will still get repeated in the union if you include all the columns, right? And then you just do a normal group by that you have.
Yeah, so you can't do the aggregation within the union, but after the union kind of takes those together. But the reason why that wouldn't work is because if you have a product name in A and a product name in B and they both have the same stock count, it'll get removed. So you need to use a union all in that case, where there is a duplicate. I mean, it's rare to have a duplicate, but it's not insane to think that, store A has 5 boxes of Captain Crunch and store B has 5 boxes of Captain Crunch. Anyways, so yeah, that would be a case for how to do that. Does that answer your question? All good? Okay. Any other questions? Okay. I need to take a sip of coffee before this one. Relational algebra is not that bad. The problem is that it's a very different way of thinking it again, and it's just annoying. And you don't want to be using it a tremendously large amount at all compared to SQL on the job, working in a real world job. And so the whole point of relational algebra in this course is that you cannot understand how a relational database management system actually does what it does without knowing relational algebra, number one. So it makes you a more powerful user. It removes the leaky abstraction idea from a relational database system somewhat. And it really kind of helps you to understand what the query optimizer is doing, because at some point in time, you're going to need to optimize a query, and it may not be just a trivial optimization. It might be a complete need to rewrite or rethink the way that the relational database system is actually doing something. And so understanding relational algebra gives you insight to how it works, because every time you submit a SQL statement to a relational database system, it takes a SQL statement and turns it into a relational algebra statement. It's from that turning it into a relational algebra statement that it can actually start to begin to do what it does, getting you data from disk or from the solid state drive or wherever it is. So for that reason, it's important. You'll never learn about it in a SQL boot camp. So from that point of view, it also makes you more of a powerful user than just anybody who learns SQL to learn SQL. You don't need relational algebra to learn SQL. You do need relational algebra to understand databases. So it's a really good thing to learn. And I want to introduce it to you because you're probably going to forget it the week after class is over, but you at least know where to go look. And you'll have my slides, and you can learn this stuff if you need it. OK, so when we talk about relational algebra, we're talking about like formal query languages. And in formal query languages, there are things that are relational algebra, and there's things that are relational calculus. SQL is relational calculus. Okay, so SQL lets the user describe what they want rather than how to compute it. And SQL is non-procedural and declarative. This SQL is a relational calculus. So we've been learning relational calculus, or at least a flavor of it. Relational algebra is like Python, not syntactically, not that you write relational algebra code, but it's like Python in the sense that you are telling the system how to get what you want. So this is now another new way of thinking. It's procedural, imperative. It's used for representing execution plans, like I was talking about. When you submit a SQL statement to a relational database system, it takes it and turns it into an execution plan, and then goes on and executes it. Now, the computer isn't like running relational algebra as the code to get data. It does that in C, which gets turned into machine code at some point. But it's using the relational algebra as a way to express the pattern and format in which to go retrieve the data. And once it comes up with an optimal relational algebra scheme, it will take it and then go ahead and execute that code using C or C++ or however the database system is implemented under the hood. So I kind of already talked about this stuff, but yeah, this is just here for your own personal edification and mine. So remember back to algebra. We have these things called operands and operators. Operands are kind of like your tables. Operators are things that are kind of like what you're doing the operation with. So like in this case, it'd be a plus sign. This holds true for relational algebra. In this case, the operators are things like union or intersection. Operands are the things, like I said, like the tables or sets of numbers or a scalar value, something that you're gonna use. So not like anything difficult, but just keep in mind these two things because they're important, because how you build relational algebra statements are by using operands and operators. Let's see. Yeah, this is pretty much everything I already said. In this class, I'm not going to ask you to create, so you can write a relational algebra statement, and then you can turn that statement into a query tree, which is what the computer is doing for you. We won't ask you to actually create the tree in this class. The statement is just enough, especially in the homework. But know that these things can be described as a tree, and they often are in as far as the computer is concerned. You're also going to have to brush up on some of your Greek symbols, because we're going to use some of those. Let's see. So there are this idea of sets and bags. Bags are multi-sets, in which case there could be duplicates. When we talk about bags and sets, we're talking about like groups of tuples, and that's how we get kind of like duplicates, not duplicates. It's this idea of bags and sets. You can do relational algebra on sets, but you can also do relational algebra on bags. That's called modern relational algebra. And every single modern relational database management system works on bags, not sets. So when we learn relational algebra in this class, we'll start by learning it on sets and using the very base kind of stock relational algebra, and then we'll expand our relational algebra with new operators, and that's when we'll start working on bags. But no, in this class, just as a reminder, when you're doing your homework, that everything we do, we're allowing there to be duplicates and stuff. So keep that in mind. And these are just kind of like information slides for you to look at and to think about. But when you think about like SQL and what you're doing, in order to be able to do like a Cartesian product, you have to be able to allow for bags because there has to be the ability to have duplicates in the system. Okay, so here are the main operators except for row rename. That's not part of the main ones, but I just include that in there because it's so commonplace. But join, product, projection, selection, difference, intersection, and union. These are the traditional relational algebra operators that we will use on this stuff. And union, intersection, difference, we've already kind of gone through that. So we'll see how those work. Selection, sigma, projection, pi. Then you have Cartesian product or join, and then rename. Selection and projection will kind of confuse you maybe a little bit because they're opposite from what you think they might be. So we'll spend a little time on that. But these are the things that you have to, don't bother memorizing them because you have access to all of your notes in this class when you're doing exams and whatnot. But these are the things that you're going to use to build your relational algebra statements. So for example, union. If we have relation 1 and relation 2, this is how we'd write the relational algebra statement in the very top right there. So just R1 union R2 with the union operator keyword. On these relational algebra slides, I put the SQL equivalent and then the pandas equivalent just to kind of like force this idea of you having something like a landmark that you've done before that you can point to understand what the relational algebra is doing. So again, with the union, nothing difficult. We've already done this. In the same aspects of the union statement apply for relational algebra as well. This might seem like, what the heck are we doing? There's just like R1, U, R2. What does that even mean? We'll write some relational algebra statements, and then we'll show you in the demo how like you can actually exercise this in a coding environment. But for now, just know that if you want to write a relational algebra union statement, this is how you'd write it in the top right. And it's similar as if you're going to write it in SQL, except now you don't have the ability to have these like tables that you can try. You have to kind of keep it in your mind. But that's how you write it. So we'll go over some examples in a little bit. This is how you write the minus, and minus is the same exact thing as except. So in this case, minus and except number are the same thing. It just depends on if you're using one relational database management system over another. In relational algebra, this is the difference operator. And in pandas, this is how you would write a difference operator, or how you write minus or except. And I just wrote some extra things there for you to read, but not really tantamount to understand the relational algebra stuff. Anyways, this is essentially kind of like a left join without the foreign key constraint. So this is how you write a difference operator. Intersection, same thing as with union. Similar to an inner join in pandas, except pandas has the constraint that those IDs have to also match. And selection is where stuff starts to get a little bit tricky. So we have a select keyword in SQL, and the select keyword allows you to select attributes. Selection is not a selecting attributes in relational algebra. Selection is the where clause, essentially. So when you're making a selection in relational algebra, you are setting conditions from which would typically be in the where clause on the relational algebra statement that you were writing. So in your selection, here we have R1 is assigned to the selection of whatever the condition is, which is the C there. And that can be a comparison operator or a logical operator, doesn't really matter. And then it's against some other relation, in this case R2. So this is how you would write selection in relational algebra. Okay, so what does it actually look like? So let's say we have this table movie here, and we've got Pirates of the Caribbean, Lion King, The Dark Knight. Here we have S1 equals a selection of year greater than 2010 on the relation of movie. That returns to us the Lion King, because it's the only movie from the movie table, which was done after 2010. So all we've done to do this very, very simple SQL query, like to all of you, this should not be a hard SQL query. This is monumentally easy at this point, right? It's just to select from with a simple where condition of year being greater than 2010. That's it. That's how you'd write it in relational algebra. S1, which is this new relation that we're creating, is equal to, or is the selection of year greater than 2010 on the relation of movie. Similarly, we can do the same thing going the opposite way with S2, year being less than 2010. So these are how we write relational algebra statements, just like this. So when I say like it's up there, right, these little like things, this is exactly what you're writing. Nothing different. OK, so before we move on, any questions so far on all this? And maybe not from like a syntax point of view just yet, but from like a logical, conceptual point of view, does this stuff making sense a little bit? Right, like here we're actually telling the data, like the system, how to get this stuff. We want the selection of year greater than, of movie where the condition of year is less than 2010. And you might be saying, oh, well, yeah, Kyle, no shit. It's no different than writing that in SQL. And I'm like, yes, you're right. It is no different than writing in SQL. But when this stuff starts to get more complex, there is a difference because you just can't rely on SQL's magic to do stuff. You have to be very exacting in what it is that you want to do because you are telling the database in a very terse way, I want this data and this is how to go get it. So when these get more difficult, you'll start to see that slight divergence like, oh, I can't necessarily represent this so easily in SQL. Yes?
The point is of this whole like notation is like keep track.
When you say keep track, what do you mean exactly?
So like, if you're writing a really complicated query, to like keep track of what you're dealing with.
Well, it's not a print statement, and you don't use them side by side with SQL queries like that.
Yeah, I just don't know like when this would be helpful outside.
That's the old like, why are we learning this stuff question. They ask you not to ask one question in class. It's that one. OK, so where is this stuff useful? So in this very like simple case, it might not seem very useful. But when you have a very extremely complex SQL query and it runs very slow, you might be asking yourself, why does this run slow? And if you can take that SQL query and rewrite it in a relational algebra query, you might uncover some interesting things. You might say, like, oh, there's a really interesting way to look at this logic if I can write it in a slightly different way. And that can help you to rewrite your SQL code in a more optimized manner. So that's where it kind of helps you. It also forces you to have a really good understanding of the underlying data, too. You will probably, like, the thing, though, is that you're not going to be able to take, like, your database and put it into a system and write relational algebra statements against it, like you will in this class, because we wrote an autograder for relational algebra. And so, you won't really get to do that on the job, but you can rewrite. There's no SQL query that can't be rewritten as a relational algebra statement. Like, it's an incongruency. Like, you can't craft a SQL statement that can't be rewritten as relational algebra, because unless, of course, the SQL statement's like syntactically incorrect or something, because the relational database system is always going to take your SQL code and turn it into a relational algebra statement anyways. So you being able to do that yourself just gives you a little bit of an insight into what the relational database system is going to do anyways, and so that can help you to write better quality code or to really optimize something, because you can see what you're doing, and you can say, oh, this is not a very good way of doing this, because when I write the relational algebra out for it, I see there's a more clear way to do it. That's a lot of hand waviness, but that will hopefully start to make sense as you write more complex relational algebra statements. Now, full disclosure, the reason why we did the autograder is because in the homework, I don't like to like kill you all with relational algebra. There's like some long ones that could be maybe like 6 or 7 or 10 lines of relational algebra. But I had one that was like 1 line, which should have been 4 lines. I made a small mistake. But this one student wrote like, it was like 60 lines of relational, or 50 lines of relational. Can you believe that? 50 lines? It was insane. It was insane. I think Vinith like turned his computer off when he saw it. He's like, he didn't want to deal with it, because he had to grade it. So yeah, I mean, the point is that you can really like go off the rails with this stuff, but if you have to like write a relational algebra statement that's 50 lines long to solve something that we solved in 4 lines, there's a grave misunderstanding of your approach to solving that problem with the query. So learning this stuff also not allows you to be able to use it down the road when you want to optimize something. And we'll show you some examples of that later on. But it allows you also a very unique insight and glance into how the relational database system actually works, and it teaches you a more thoughtful approach to just writing better quality code and queries. So it's just, those are all good things to do. It's not just because this is UCSD and I have to make it difficult for all of you, and so I'm going to give you something difficult to do, though I don't hold that against me, because it sounds like a fun way to spend my Thursday and Tuesdays. But yeah. This stuff is just good to know, and it makes you a more powerful user of relational database management system. Plus, if you're going to go into like data engineering or you want to go into database research, this is going to be your life. So this kind of stuff. So it's also some interest there. I'm sure some of you will want to go into database research. Don't look at me. OK, so good question. Was there any other questions about this so far? OK. Does everybody understand the logic behind this? Is that all good? We all get it? OK. OK, so let's look at projection. Projection is the select statement, or the equivalent of a select statement in SQL. So pi is the projection symbol. And we're saying here that we want to project, we want to select attribute A1 through whatever from R2. So projection is a select statement, and selection is a where clause. Like those are the equivalencies. So projection is just a select statement. Again, I put down that pandas code down there to kind of help ease all of you into them, and so you can understand what's going on. But yeah, all you're doing is selecting attributes. So here's an example of this. We have the movies table, and we want to be able to select genre from movie. So we would do S1 equals pi subgenre of the movie relation. And if we're looking at set semantics, we get duplicates. It will automatically remove duplicates for us. But if we're using bag semantics, like what most relational database systems use today, you're going to get duplicate genres. So here's a key insight. This right here, the difference between bag semantics and set semantics on this query is proof that you need to use a distinct keyword in modern relational database systems, because it doesn't get rid of duplicates tuples for you, right? Like if PostgreSQL was going to return to you this for a simple select genre from movie query, if you did select from genre with PostgreSQL using that table, and you got this, it would show to you that PostgreSQL is using set semantics. It does not. It uses bag semantics, which is why you'd get that result over there, which is why you would need to use the distinct keyword if you wanted to get the result on the right from PostgreSQL using this query. So again, it just gives you more insight into what's going on and why. Perhaps not a very interesting example, but an example nonetheless. OK. And then here we have the Cartesian cross product. Big surprise, it's a big X. X marks the spots. And that's just the SQL equivalent of select star from R1, R2. So if you want to do the Cartesian cross product, you would just do this. And of course, there's also naming conventions that you can add. So R1.A, R2.A, that stuff still applies just like it would in modern like SQL queries you write. You can use these type of qualifiers on the table names to get a little bit better sense of what you're doing. But yeah, cross product, that's all good. And here's an example of it. I don't have the relational statement here, but if you just look at the movie X acted in to the right, that's essentially the relational algebra syntax you'd use to write the Cartesian product of these two tables. So here we have the Cartesian product of the movie table and of the acted in table, which means we have 2 and 2, gives us 4 for the Cartesian product. And of course, here we have some tuples that are not quite right. So Pirates of the Caribbean did not have Christian Bale in it, correct? Yet we have Pirates of the Caribbean, 2007, action, Christian Bale, The Dark Knight. So this is what I mean by being explicit. If you were to do just the natural join or the inner join in PostgreSQL, it would do a join and it would not give you this table. It would do this table under the hood maybe as part of its computational step, but then it would give you a filtered out result on the IDs. In relational algebra, the Cartesian product does not do that for you. It just gives you this big result. It's up to you to do the filtering manually. So it's very much like you've asked it to do the cross product, you're going to get the cross product. In SQL, when you do the cross product, the inner join, you get the inner join. The cross product is just the intermediary step, and then it does the filtering for you on the IDs because it's doing a join. So that's how Cartesian product works a little bit differently than when you do it in SQL. Okay, so that's Cartesian product. Renaming, super simple. It's just row with A, B, C, and that's the renaming you want to do for the table, for the attributes in the movie table. Yeah, pretty simple there. And let's try some practice problems. Well, before starting practice problems, are there any questions? Yeah. Mm-hmm. Yes, projection is just selecting. Mm-hmm. Are they ever going to be nested together? Well, yeah, I mean, you can nest all this stuff, but in principle, they're doing separate things because when you do selection in relational algebra, you're filtering tuples, so it's like a row level filtering. So that's like the where clause, whereas projection is filtering out columns. So that's all. It's just, I say it's confusing because when people think of selection, they think select statements. But don't do that. Relational algebra is not that easy. But yeah, no, good question. Any other questions before we do a couple sample problems? Okay, so go ahead and get with your friend and try to write the relational algebra statement to retrieve movies after 2007. Yeah. I promise it's not that bad. See, the problem is that the people on the live stream don't, or the podcast don't see other people laughing at my jokes, so they just think I'm this idiot up here who's like laughing at his own jokes. That's okay. Okay, who wants to help me solve this? What's the first thing we need? Sigma? The sigma selection thing. Are you sure?
It's like you're trying to do where the year
Yeah.
is. Oh.
I'm trying to build confidence in you. No. You should be like, yes, damn it, it is selection.
And then a little like subscript
Yeah.
year greater than 2007.
Uh-huh. And then that's just also for the,
Parentheses.
yeah, exactly. That wasn't so hard, was it? It was not too bad? I told you I was going to give you a heart attack in class, didn't I? There's nothing more lonely than like looking towards people for the answer and no one, everyone. I look at Vineet sometimes and he looks away from me. I'm like, you can't do that. Okay, so this is, yeah, easy. Okay, does anybody doubt this, or is this all good? Good, okay. Let's do another one. How about this one? I wrote this long in mind. Not needed. Yeah, because this is a, yeah. Okay, who wants to help me? Yeah. It was, yeah, exactly. Ever go with this one? Okay, let's do another one. Okay, so what kind of relational algebra operator are we gonna need to use? So that's gonna be, yeah, exactly. Okay, and then what am I doing sigma of? Yep, and what condition?
Equals action.
Exactly, and on what relation? Yep, exactly. So again, not terribly too scary. I mean, you know, this is pretty basic stuff, so it shouldn't feel too bad. It will get harder. Vineeth has made sure of that. So when it comes to set reviews, you know who to blame. No, but yeah, it's just you have to be able to think about your relational algebra query as like something that's like it's like a Russian doll kind of thing where it's like layers within layers within layers, and you're kind of like unwinding it. Like that's a way to think about it. You could also do interesting things here, like the person who did the 50 or 60 line answer is because they forgot that I said that you can use a constant, like a number in relational algebra. So instead of like just using a number 0, they did some long calculation thing to get that number 0 from the data. So you can just use the number 0, right? Because in SQL, you can use a constant, and there's no SQL statement that you can't rewrite as relational algebra. So anything you can write in SQL, you can write relational algebra. So if you're really struggling to think, try writing it in SQL a little bit, and sometimes I can kind of help you to see the logic. Okay, so you might ask, like, how the hell do these people create a autograder and stuff for this stuff? Here is, surprisingly, a tool called Relax. I love these names. Where it will allow you to insert a data set into this tool, and then there's like 10,000 lines of TypeScript code that it uses to allow you to write relational algebra statements against it, as well as SQL statements, and it will tell you whether it's valid or not. So you can put toy data sets into here, because it's all done in the web browser, so you can't get too large. But this will allow you to practice this stuff and exercise it, and all of our demos will be based off this. The cool thing, though, is that we ripped we ripped the engine out of this and then repurposed it for a relational algebra autograder where you can write the same syntax you would in here, so you can use this to practice and do your homework, and even on the midterm and final, or not the midterm, but the final. And you can write those statements, and you can see if they work, and then you can submit it to us, and then we'll run it through this autograder. And the way we do it is we take this engine and we turn your relational algebra into a SQL statement, and then we pass that into our other autograder for SQL. So we're kind of like dog fooding our autograders, which makes me extremely happy as an engineer to see that happen. So we're going to go ahead and get started with the demo. Please all go to the Relax website and play around with it. We'll show you how to. It's not a very friendly website, and it can be very difficult to figure out how to put data in there and get it working because it doesn't give you very good feedback. But once you get used to it, you'll get used to it. And yeah, we'll be good to go. So why don't you take like a minute break while Vineeth sets up, and then we'll get started. right, the ship is yours, so to speak. Maybe?
Shouldn't take too long. Yeah.
Okay, we'll start with set operations very quickly, and then we'll jump into relational algebra.
Okay. Right. So we looked at set operations, like a specific example that I can give from one of the previous demos, where we could have used set operations instead. Is this example? So we had this one example where we had to retrieve all actor names that have acted in at least one movie which has both action and sci-fi as genres, right? So in this case, what we did was we used a self-join, right? So again, I think you should be pretty familiar with the IMDb schema by now, so I didn't put it up again. But from the schema, you looked at, you wanted both genres, action and sci-fi. So you had to, join movie genres twice, right? And then make sure that the movies were the same through their ID, and then say that the genre was action for the first movie and genre was sci-fi for the second movie, right? So this was the query that you wrote. Does anyone have a solution that you can think of where you just use set operations instead, right? Something to simplify this query, like thinking of the self-join might have taken some time, like, you have to get pairs of movies, then figure out and then do it. But from the lecture today that you learned, yeah, what do you?
Like take the data set of actors who have acted in action movies instead of actors who have acted in sci-fi movies and take the intersect.
Yeah, that's pretty much it. So the idea is basically using the intersect. All you do is you write two separate queries, right? You just say that, take all the actors who have acted in action movie, take all the actors who have acted in sci-fi movie, and just intersect those two results, right? Much easier to write this than thinking of a self-join and like trying to figure things out, right? So let's say, think of a case where you were not just asked action and sci-fi, but you were asked like action, sci-fi, and adventure, right? So then your self-join becomes even more complicated because you're combining like 3 movie genres tables and trying to get the information, right? Instead, if you simply use intersect, where you're like, okay, you take the first one, you take the second one, join them, then take the third one, join them. That's much easier to write. And you can kind of repeat the names. So in this case, you can notice that I've said that from actors and named it as A. And in this intersect statement also, I've named it as A. The idea here is that, these are 2 separate queries, kind of. Like, so the SQL engine just runs those 2 queries, right? And once it runs those queries, whatever output it has, like the intermediate table, it takes an intersection. And as we discussed in the lecture, basically if the data types of the columns match, then it will do the intersection or union, right? So that's how you would use intersect in this case. Okay.
And much more important than being easier to write, because you can always write something that's complicated. It's easier to read and refresh yourself. 3 months later, you come back and look at why you did 5 joins. Now it's just a lot easier.
Okay. All right. So what about this case where we have like find movies which have action as a genre but not sci-fi? What would you do in this case? Yeah.
Do something similar. Find the movies which are action movies. Separate table. Find movies that are sci-fi movies, and then do action data or action relation minus
minus or except, right? So yeah, so that's another use. If you did not have set operations like in your toolbox, right, then thinking of this would have taken some time. Again, you would have done like a self join, be like, okay, movie genres 1 should be action, but movie genre 2 should not be sci-fi, and the movie ID should match. So instead of that, you just use an except statement. So you just take the action movies, you take the sci-fi movies, and just say, get all the action movies except the ones that are present in sci-fi, right? So that's kind of it for set operations. For union, the basic idea is that it is kind of like a join. So in case you have too many joins that are happening in your query and you want to simplify it, right, you can just use a union instead, right? So that's the main use of union typically. Yeah, it's basically an inner join, right? So if you think in terms of sets, remember how sets work. So inner join is just like the intersection. Inner join is like the intersection after you take everything that's common, right? So okay. So we'll go to relational algebra. So there are some operations and operators that you can take a look at here. The main thing I actually wanted to cover in this is how to write relational algebra, more like, and we will go into like examples and how to use it on Relax in the next demo. But in this demo, the focus is like, get an idea on like how to write it, which is also very important, right? So one of the things that you use is called as LaTeX. How many of you have heard of LaTeX and like have used it? Okay, that's good. So typically, most of the resumes or like the documents you see online, all the PDF documents are generated using this thing called as LaTeX tool. The idea being that you write it in a clean, like a coding kind of format, and then that code gets converted into a PDF that you can be viewed. So any research papers that you see or you've read online, any textbooks that you've seen online, all of them are written using LaTeX. Okay.
And you have to learn it anyways for DSC100.
Okay.
So you're going to have to do it. You might as well get started now.
Mm-hmm. So we won't go into like what LaTeX is and how you can use it, but a typical way is just to use this online tool called as Overleaf, right? So if you go to this tool, so you can see I have a few resumes and stuff written here, but you can just create a new project and just create a blank project, and you can start working on Overleaf, right? Probably not. So the commands that are written here, like /pi/sigma, are what is called as LaTeX math mode. Okay, so LaTeX has support for mathematical operations or equations. So what you can do is you can write these operators. So when I say I wrote the /pi, right, it shows up like this in math mode. Okay. So the pi you see on the left is the actual operator, and when you write it as /pi, that's how it looks, right? And then /sigma looks like this, /rho looks like this, and so on, right? So you have these different operators, right? And how do you go about writing them, right? So let's just quickly, before we go into the next one. So this is Markdown, so in Obsidian that we are using, these are all Markdown files. Not you guys, what we are using. So Markdown, some Markdown support math equations like LaTeX. This is one of those cases. GitHub also supports the same thing, like whatever Markdown you write in GitHub also has support for these LaTeX symbols. GradeScope also does that too. So GradeScope, when you submit your answers also, you can put it in between the $signs and you can write the LaTeX. So as an example, so if you were to write, so let's make this a little bigger, okay? If you were to write in between these $4 symbols and say the /pi that I gave you, right? And then just move aside, this is how it would look, right? So it would center align whatever you wrote, okay? If you so this will be in a new line, but if you enclose it in single dollars, then it just puts it in the current line itself. Okay, so that's what is happening here. So similarly, you can do row, you can do sigma. Let's say we do sigma, and then this is how it looks. Okay. So yeah, Obsidian can help with that. You do the same thing, same logic in LaTeX as well. So we've given you the list of symbols and everything, right? The next thing you want to know is how to do the subscripting, right? So in this case, for example, one of our examples was saying that, you know, sigma year greater than 2007 on movies, right? So if you write it like this is how it would look, right? So the underscore here represents subscript, and anything you put in these curly brackets will become the subscript. So in this case, this is how it would look. So if you want to write sigma year greater than 2007, sigma underscore, and then you put the year, and then you put the movie name. Okay. If you want this movie not to be stylized, then you can say something like, you know, make this like a text, right? So that it looks like actual text instead of like algebraic variables, right? Same thing you can do for year as well, but yeah. So this is how you start writing your LaTeX, okay? The reason we're telling you is this is just good practice, and also last quarter we expected everyone to write the array in LaTeX, so it's a good way to practice how to write math equations, right? And this was kind of the guide that we gave, where let's say you're given this hint, this is from assignment 4, but you don't have to worry about this as much, right? But yeah, so let's say you're given like a relational algebra tree, something like this, right? We still haven't looked at joins. This will all be covered in the next lecture, joins and grouping and everything. But the idea is that you start from the bottom. This is the person living, which is one table. Then you have a parent-child, which is another table, right? And then what you're doing is, like in this case, parent-child P1, P2. When you say row P3, P4, that just means that you're renaming the columns from P1 and P2 to P3 and P4. So this is kind of how you would write it, right? So you create temporary tables. That's how I think of it, right? So you create temporary tables in between. So you say T1 equals person living, and then you put the join statement based on what the join is. You'll learn about it in next class, but a parent-child. And then you put row as this. And then T1 and T2 now become these statements here, right, at the top. So T1 is this statement here, T2 is this here, and now you're joining T1 and T2, and that's kind of what you're doing, and you're setting that as T3 and so on. So in your, for your homework 4 and like for your final exam also, you would be kind of expected to write like this, and then your final statement that you have should just be the empty, like it should not be an assignment statement. Relax also will throw an error for you, but yeah, so this is how you would be expected to write, okay? Obviously, you don't have to, this guide to this order of precedence guide is only for you to know how to write, but you don't need to know LaTeX. Relax makes it easier. So we can take a look at how Relax works, okay? And this is the reason that we use Relax, right? Usually when you're learning SQL, the biggest problem is like when you're starting out, SQL is something you can run, right? You can like write the code and run it on some dummy database and get an output. But the problem with relational algebra is you didn't have such a thing. Everything was pen and paper. Like you had to write it theoretically, write it down and see what is going on. So this calculator helps a lot. What it does is it essentially does the job for you. It helps you to run relational algebra essentially, okay? So if we go to this link, okay, so this is how it looks like. Let's go white mode for, I mean, I don't like it, but I have to use white mode in this case. But yeah, you can see that when you go to this website, it has a dummy database already here where it has these tables, R, S, and T. And R has these 3 columns, A, B, and C, which is like a number, string, string. S has string and number. T has string and number, right? We learn on how to put your own data in the next demo. But for this demo, this should be sufficient. right? And you have all these relational algebra queries as well. So you can see that pi is there, sorry, not queries, the keywords. So you have pi, you have sigma, you have rho, this you'll learn later, and then the rest of them you'll learn later. You have intersection, union, minus, and a Cartesian product, right? So idea would be something like this. All you do is you simply write, say you're taking R, okay, and let's say we just select. So you can write it like this. You can say pi. So you can look at the, hover over it and see how you have to write the query. So it says pi a comma b from A. That just means that you're taking columns A and columns B from the table A, right? So in this case, from table R, we can just say like, just give me A and B, right? And so I write it like this. So it doesn't throw any error, and you execute this query, and you can see the whole query here, right? So how the execution is going about, what the time is, what's your actual query, and also the results of your query as well. Okay? So this tool is super useful. Basically, it's like allowing you to execute relational algebra, right? So in this case, this R table has 5 rows, and then you're just selecting A comma B from R, so you get all this information. Okay? So we can do more complicated queries. Let's say you first do sigma, and then you say A equals, let's say, what was it? A equals, like, say 1, okay, from R, right? And then you can say pi on this, and then select A comma B, right? And then you can put this whole thing in brackets, okay? And then you can execute this query, right? And it shows you the order in which the operations go, right? So you can say R, and then it shows sigma A equals 1, and then it shows pi A comma B. This is how your RA would look like, and this is what the result is, okay? You can also do it in the lines like I showed you. So what you can do is say that T1 equals this, right? And then you can say select pi A comma B from T1, right? And we can execute this query, and it does the same thing. Okay, so I would recommend just playing around with this tool, getting an idea on how to use it, because homework 4 you'd be using this, and then whatever result that you write here, same like how we had our YAML files, you just put this in the YAML file, and then it should give you, it should be auto-graded. One more thing is the advantage is you can write SQL queries, although it does not support everything in SQL. So there might be some questions which you think it's easier to write in SQL and you try and write it, but unfortunately Relax does not support the proper conversion from SQL to RA. So it might not work. So it's recommended that you write in relational algebra. In this case, it's easy if you just have a simple select statement, right? You just say select A comma B from R, right? And then you execute this query. It'll still give you the relational algebra as well and the output. Okay? So this can be a nice way of learning relational algebra as well, right? Because if you find it easier to write your select statements or SQL queries, then you can go ahead and do that and then look at the relational algebra. But
there's a good documentation page.
Oh, yeah, sorry, I forgot about that. So there's this help page. The help page has a tutorial as well as a reference. This reference is important. So it tells you what the syntax is and how you can use the different operations. For example, if you look at pi, the example tells you how to use it and what it should be, like function, argument, and then child expression, and so on, right? It's a complete grammar, I guess, context-free grammar, something. Yeah. If you don't know what that is, you can Google that, but yeah. It gives you, this whole help is super useful. You can figure out what the issues are, and you can refer to this, but yeah, that's pretty much it. Any doubts still?
I mean, yeah, play with it a little bit, but we'll do it in
Thursday's demo. Yeah.
You get a question?
Okay.
A compliment, maybe?
Okay.
Well, we have like another 7 minutes, so you want to do some more?
We'll pass for today. I mean, it is ready. We can do the next demo, but that's all right. We'll give them a break.
Any questions on like the midterm or homework 3 or anything like that? Or
Yeah.
All right. Yeah. So I think discussion section on Friday will be mostly revolved around
Midterm.
yeah, taking the stuff that's going to be in the midterm and just kind of giving you a refresher about it. So if you have some doubts, you're having some difficulties, definitely go to the discussion section on Friday. And other than that, yeah, it's raining, so, or it will be soon. So we'll end a few minutes early tonight, and we'll stick around here, or if they come in out there for as long as anybody wants to keep.